So we're going to do areas and volume part 2 here. There are 3 main areas that we're going to cover. The first is 3D, since we basically looked at areas last time. So you know, squares, circles, rectangles, and that kind of thing. Areas being, you know, measured in meters squared. It's 2-dimensional. 3D is when you're talking about volumes. So here we look at cubes instead of squares, spheres instead of circles, and so on. Mathematically, it's pretty much the same thing. So as before, we'll have expressions. So the area, what's the area of a cube? It's the length cubed. With boxes, you could have generalizations of rectangles. So, you know, you'd have the length and the width of a rectangle, but for a 3-dimensional equivalent, you'd have the length, the width, and the height. So they're the kind of issues that we come across once we move to 3D. And as before, all the formulas and expressions that you need to know are in your tables book. So for whatever problem you're doing, you just look in the tables book and the formulas and expressions are given there. The other type of problem that we do is compound problems. So there, where you have some strange shape, which is, when you look at it, you go, oh well, the top bit is a square, the base is a rectangle, and it has a circle in there as well. So basically you have a complex object which consists of multiple say primitive objects. So the thing whose area or volume you're trying to determine is not in your tables book, but it is made of maybe 2, 3, 4 things, each of which are in your tables book. So, you know, you just need to work out the area or volume of each of the primitive objects that we're dealing with. We'll do some examples and you'll be able to see how that works. Also, there is the Trapezoidal Rule. So this is actually a numerical method. and it gives you an approximate solution. Now you might be going, well, why would I want an approximate solution when we have exact solutions so far? You know, when we work out the area of a circle, the answer we get is exact. I mean, if the circle has a radius of whatever we say it is, then the area is pi r squared. I mean, there's no roughness there. The reason that we use the trapezoidal rule, or that we'd want to use an approximate rule, is often the thing that we're dealing with isn't a primitive object. It isn't a circle, a square, or a rectangle. So you might have something that's like that. That's not a circle. You can maybe go, I'll break that into some rectangles. You know, so I can go, oh, that's, if I say the first part there is a rectangle, something like a rectangle there, I'll say that bit there is a bit like a triangle, and so on. It'll be pretty clumsy, but you can kind of get an approximate estimate of the area under that curve. So, you know, that shaded region. Well, the trapezoidal rule is a systematic method which is pretty accurate. So it's a good balance between being useful and easy to apply and being good. So by knowing the trapezoidal rule, we're able to determine the areas and volumes, or areas, because we only do the two-dimensional case. We're able to deal with general objects, more complicated shapes. So we're not restricted to just dealing with circles, squares, and triangles. Now they're the three main topics that we're going to be looking at, though there's also some miscellaneous things on the side. So in particular, there's the idea of nets, which is kind of like if you were to cover, say, a box with wrapping up paper, and then you were to look at what that looks with the shape of that. We'll come around to that after we've done the main order of business: 3D compound objects and the trapezoidal rule.